This is the continuation of a question that I'd started earlier, but this part involves the central limit theorem. In a computer simulation, random samples of size 200 are repeatedly selected from this population. Here's the population distribution. And the mean of each sample is recorded. 1,000 such sample means are recorded. Describe the expected distribution of these sample means. Your description should refer to the shape of the distribution and to its mean and standard deviation. So here's the population distribution. The mean is 22.05. That's the balance point. That's about here. The standard deviation, sigma, that's a lowercase sigma in the Greek alphabet, is 10.64. What we're doing is taking samples of these x values. So all of these values here are the x values. So they range from 0 to 80. And, you know, there's probably tens of thousands of these values because there are tens of thousands of employees. These values represent employees' earnings for the month of 2009 in Ireland. So you can look at earlier videos to see the start of this question. But anyway, we don't really need those details too much. We just need the mean and standard deviation of this distribution. What we're doing is we're taking samples of x, and each sample is size 200. So little n is the sample size. So as I said, the population of values capital N is probably some very large number. It might be 100,000. We don't know what it is actually, but we know it's some extremely large number compared to our sample size, little n. And what we do with each sample is get the mean. So we might have one particular sample size 200, we calculate the mean, that's denoted by x bar, we might call it x1 bar, because what we do after calculating x1 bar is we throw the sample of size 200 back into the population, pull out another sample of size 200, calculate x2 bar. That's the second sample mean. So each of these sample means would be calculated by summing all the x values and dividing by 200. So we'd sum a different set of x values here, but we'd be dividing by 200. So we keep on doing that ad infinitum in theory, and we have all these sample means, and we just see what the distribution of them looks like. So I explained all this in the previous video. I'm just repeating myself really. We found that if we look at all the sample means, now x bar are all the values along here, we'd find that most of those values would be in or around the population mean, which is 22.05. So that's mu. So we'd find that most of our x bars would be in around this, with few of them far from it, far to the right of it, and few of them far to the left of it. We'd actually have an approximately normal distribution centered at mu equals 22.05. The standard deviation of this normal distribution will be given by sigma over the square root of n. So here is sigma for the population distribution, which is 10.64, divided by the square root of n, where n is the sample size, n is 200. So this thing is also known as the sampling distribution. This is the distribution of sample means. So by sampling distribution we mean the distribution of sample means. In this situation we're talking about sample means. So the sample means are along here. Just as an aside, notice that if our sample size gets bigger and bigger, suppose we add another 0 onto this, so we have the square root of 2000, then the standard deviation of this is even smaller. So the standard deviation of our our sampling distribution is this thing here, sigma over root n. By making n large, we see that the standard deviation sigma over root n goes down. So if n goes up, this arrow means n is going up in size, then sigma over root n is going down. So this actually becomes narrower. So if I was to increase n, if I had a sample of say 2000, then we'd have a much narrower distribution. So we'd find that our sample means are even closer to 22.05. So by making the sample size n big, we can get a more precise estimate of our unknown population mean. Normally the population mean mu is unknown. We use our sample to infer roughly where our unknown population mean is. How many of the sample means would you expect to be greater than 23 euros? Now I took this question from the sample papers. So 23 is greater than 22.05, so it's about here. So how many sample means are greater than it? So here, this green region represents all the sample means that are greater than 23. So what proportion? Let's consider the proportion first. Forget about the amount. Forget about the how many. Let's just consider the proportion of sample means that are greater than 23. That's this area here. The total area underneath a probability distribution is 1. So to find this area here will involve going to reading normal tables. That gives us these areas. But first of all, we must convert this to a standard normal distribution to get this area. Once we found the area, then we can get the actual number of sample means that are greater than 23 euros, because we're told in the question that 1,000 sample means are recorded. So if this number here is, if this area here is 0.0, say it's 0.1, that means that 0.1 of all the sample means are greater than 23. Since we have 1,000 such sample means, we multiply 0.1 by 1,000. So that's the idea, and that gives us the actual number of sample means from our sample of size 1,000 that are greater than 23. So we just have to get this area, so we need to convert this thing to a standard normal distribution. So I'll just draw that underneath here. A standard normal distribution has mean 0 and standard deviation 1. Mean is at 0. Balance point is at 0. So what we need to do is convert 23. So 22.05 is transformed to 0. What will 23 be transformed to? So we have to see how many standard deviations 23 is from 22.05. Now I've covered this in other videos. The formula we use is x minus mu divided by sigma. X minus mu actually gives us the distance of our x value. Well, actually it's not x here, it's x bar. I suppose I better just to be careful not to confuse it with x values from our population. We're talking about x bar is our horizontal line here. We're dealing with values of sample means. So x bar minus mu is the distance, absolute distance, and we divide by sigma. That counts the number of standard deviations. So x bar is 23. Subtract the mean, which is 22.05, and we divide by sigma, which is a standard deviation, except it's not 10.64, it's 10.64 over the square root of 200. That's the standard deviation of the distribution of means, our sampling distribution. So we have 23 minus 22.05, and we want to divide that by bracket 10.64 divided by the square root of 200. So we close the bracket on the denominator and we get 1.263. I'll round it to 3 decimal places, 1.263. So 23 corresponds to 1.263 for our standard normal distribution. And these values here are the z values. The horizontal line represents the z values. So we read down a z value of 1.26. So we go to 1.2 and we go across here and read under 6, which is this value here. Okay, so we go to 1.2 here and we read under 0.06. So this gives this row up here gives the second decimal place. The second decimal place is 6. Actually, we don't need a third decimal place. We only need a third decimal place to see what the second decimal place is. So it's 1.26 we have here. So the area to the left of 1.26, that's this shaded area here, these tables give the area to the left of Z, is 0.8962, which means that the area to the right is 1 minus 0.8962. The total area underneath a probability distribution is 1. So here's our answer, 0.1038. So that's that area there. Now I might have mentioned 0.1 earlier. Well, that was just a guess, but it's actually quite close. So that's the proportion of sample means that are greater than 23. And I said earlier that we have 1,000 such sample means. You can barely see it here. We have 1,000 such sample means. So we have 0.1038 multiplied by 1,000. So we get an answer of about 104 means, sample means are greater than 23.